pre-lunch lecture was to deal with single pile. Yeah, but as I was saying yesterday, very rarely single piles are used in practice. It's always going to be pile groups. Now, pile groups sitting in laterally spreading soil are a real concern. So, one of the mechanisms we envisaged, as I said before, is to do with this 4-hinge mechanism. If it's a 2x2 pile group, there are 2 other piles behind it, but you can say that is a kinematically admissible mechanism, right? So the piles deform in the liquefied soil and the whole thing spreads that way. But when you have this is like a idealized case where I got some bedrock into which I can rock socket the piles. Now, most cases, most general cases, foundations are placed into some, you go through surface layer and you go through liquefiable layer, and clearly this is loose sand, so you're not going to terminate your piles into loose sand. You'll find either dense sand or stiff clay below it, and you drive the pile into, and the pile tips in there, right? Now, if this is the case, what will be the failure mechanism, right? So, although these are easy to calculate, these are not the most general case. So working out the buckling load for this, you have already done. So this is easy calculation to do. So first thing, when you're designing piles, you want to make sure is, do the buckling calculation, make sure that your buckling load is maybe 7-8 times larger than the actual load you're going to apply, so that the piles will not buckle. This is the same approach a structural engineer will take when they're designing columns, right? When the columns are being designed, they'll check for the buckling load. If it is coming anything like 2 times or 3 times of the load that column is going to carry, they'll get scared. So what they'll do is start designing some struts, horizontal struts to support the columns. So quick check, make sure that doesn't happen. Then you will have this kind of situation where you have non-liquefiable layer on the top, liquefiable sand and dense sand. So what is the mechanism we expect here? We expect that the pile will now translate a bit horizontally, but also settle a bit. So the moment I can get some settlement into dense sand, then my tendency to buckle will go away, because I'm no longer imposing zero displacement at the pile tip. So these kind of piles very rarely will buckle, because the buckling load will be a lot higher, and if you are applying anything like that, it's easy for the pile to settle. That doesn't mean the pile won't have bending. The pile will still, it's settled, but also it is trying to bend a bit. So you're still in the bending regime I've shown you in the morning. Okay, so you get some settlement and some lateral movement and also some bending, because this obviously doesn't move laterally as much as this can. This one is going for a ride with this layer. This is sitting on liquefiable layer. We talked about formation of water film here, which means this is trying to go a lot. But the tip of the pile doesn't like traveling that much in dense sand, because if you try to shear dense sand, it will oppose that even more strongly, because it can dilate even strongly, more strongly than the liquefied soil can. So this is a plausible and more realistic mechanism. Okay? And this is where we can do some fairly simple calculations. So, say you are in level ground to start with, you can say the non-liquefiable crust is going to apply the full passive pressure. So for clayey soils, you know how to work out Kp. Yeah, you should have done that as maybe third year geotech or fourth year undergraduate course. How do you work out passive earth pressure for just clay? Yeah, if it is sand, it will be 1 plus sine phi by 1 minus sine phi. If it is clay, what should it be? Anybody remembers? 2Cu? Okay, okay, so that we can very easily calculate. These layers are always going to be fairly of limited thickness, maybe 1 to 2 meters. So although I am applying passive pressure, that triangle is going to be fairly small. Okay. In the simplest of cases, we can say the liquefiable soil, as it is trying to go towards the pile, is applying some kind of uniform pressure. This is obviously simplification. In reality, it will be some kind of a trapezium, right? Let's keep it simple. It's already liquefied. It has to dilate as it goes past the soil, goes past the pile, and let's say that for simple case, we'll say take that as uniform. And at the base of this, between the bearing layer and here, you can apply some torsional spring with some rotational stiffness be applied, which is Kr. Okay? Right. So now I want to draw the equilibrium of this pile. So what are the forces acting on it? The forces that are acting horizontally are the liquefied soil pressure. You can use Go and O'Rourke, Tom O'Rourke and Go approximation. Work out what this is, apply that as a uniform pressure, and say, and that times the outer diameter of the pile. Because the pile is going to be like this, the soil is going to come, so the projected width is d naught, right? So that will be, so I am multiplying with the d naught, then this is the pressure distribution. At the base, I got some shear, at the interface, I got some shear force Fa, a bending moment of Ma. So at the top, I got another shear Fb and a resisting moment Mb. So this is like now a beam on which I got uniform pressure on one side and I got the shear forces and the resisting moments on the other side. One thing that we have added here, and this is the new bit, is the actual load the pile is carrying. So we should not forget this, because these piles which are on slopes are not just there for fun. They are carrying some actual axial load. Why is this important? The moment this pile is going to try and bend outwards, I'm going to get that P times delta as an extra moment. So every element on this pile has to work to resist that P delta effect. Okay? So this is the equilibrium of forces. And the thing we can play with is the EI of the pile, because that's what it has. It has flexural stiffness. E Young's modulus, I is the second moment of area. Do they still call I as moment of inertia? Second moment of area is what it should be called. But when I was growing up, we always called that moment of inertia. Because it has no density term, it's not mass moment of, there will be some 2 by 2 pile group, so there will be other piles here. So because of the frame action, structurally, these piles, one will go into more compression, the other one will go into tension. That has to happen. That is just structural mechanics, right? So, in fact, the settlement in the pile group, if I go back, it may be that one of them will settle a bit more than the other. Okay? So I can write these equations here to, first of all, the moment equilibrium and then the force equilibrium. That's all these are. F crust, I can say what is the stiffness of the crust layer, and then how much does the crust wants to move minus how much the pile is allowed to move. So that is the relative displacement between how the crust movement and the pile movement, pile cap movement. So that is how much force due to crust will come on to my pile cap. Okay, so these are fairly straightforward to write. So FA simply is the difference between the moments plus, if I take that as uniform pressure, PLD L square by 2 because it's a distributed load, minus P delta over the length of the pile in the liquefiable layer. So that's what we are calling LEQ. Okay? FB will be minus FA because it's opposing that movement, plus so this is basically, this is the moment equilibrium, this is the force equilibrium, horizontal force equilibrium. So there you go. So this kind of thing we can do very easily, right? So even if I assume some kind of a trapezoidal distribution here, I can still adjust those equations to account for that. We know how to do forces acting on beams is something we learnt many years ago, and they're very easy to apply. Okay? For moment equilibrium, you can also simplify those equations by using mu, which is nothing but square root of axial load over EI. So this is almost telling us what the load applied force P is, or load P is, relative to its flexural stiffness. Okay? And basically, if you plug these in, the mu's, it will become fairly obvious. It's going to come down to the P delta effect there as well. Then you can do this kind of limit equilibrium analysis where I'm plotting along the x-axis some mu. Okay, if my mu L is very big, then F delta will become small and FPL will increase. So that bit we've done assuming the pile is completely going to remain elastic, because we are simply applying the forces and it's all elastic analysis, right? However, we are also interested in when the pile is actually going to fail. So what you want to think about is, what is the delta I'm applying to the pile compared to the force from the crust. So the limit for this is the passive limit that you are mentioning. So that is, the soil has to yield beyond that point. But many times the structural failure, so it will behave linearly up to there, and then it reaches some plastic MP value for the pile, and that is what causes structural failure. Now this point here is when the first yield occurs. So in elastoplastic analysis like this, you simplify the whole problem by saying, well, I got the elastic bit and I got the plastic bit. You do not take the increase from first yield to peak and then softening. For steel piles, that can happen. But you ignore that bit and say, that is the factor of safety in my back pocket. So that is normal plasticity assumption. Now, what you have here is how much is the crust wants to move, which we calculated in the first lecture. So this is how much the crust wants to slide down due to lateral spreading. Yeah. And versus how much the pile wants to move. We said the relative displacement is the important bit, right? Now, one thing you want to make sure is if I draw a line 1 in 1 with a slope of 1, that means the pile movement and the crust movement are exactly the same, right? So, if that is the case, the pile should not see any force. Displacement is more than the pile displacement, right? That's when trouble begins, because that's when the soil wants to move more, the pile doesn't want to move as much, therefore the soil will collide with the pile and therefore will create the extra earth pressure. So it's a simple way of looking at that, by looking at how much is the elastic deflection I get for the pile compared to how much cross displacement I can estimate using something like Newmark sliding block. Okay. If this is the case, we are designing for the pile to fail way before the soil will fail, right? But imagine that my soil is, the crust soil is weak. It's not very stiff, non-liquefiable layer. It's fairly soft clay. Then the structural failure will happen much higher compared to the soil yield. So the pile will stay where it wants to, and the soil is going to try and flow past around it, and therefore will apply the full passive pressure, whatever it can. So again, we'll take this linear bit, and it can't go past this because the soil has failed. So this is the limit of the what the soil can apply as a force, right? So you stop there and you go down here. Now what you have is this crust displacement here, pile displacement here. If I come down here, this is the 1 in 1 line, and basically I'll come up to here and my crust displacement increases while the pile displacement doesn't change anymore. Does that make sense? Because the soil has failed, therefore it can flow. So the crust will continue to deform or go down the slope, but it is just going around the pile. And the pile says, that's okay for me, I'll just sit there. So you won't get any increase in delta, the pile tip displacement anymore, pile top displacement anymore, while the crust displacement increases. Okay. Now what we want is, all this looks great, but based on some, as I said, all we have done there is mechanics again. But those mechanics are underpinned by X32 maybe. Circular section D. So MP is going to be ZP times yield stress. And for circular section, ZP is pi by 32, I think, D. Is it 4 or 3? 3. Anyhow, any structural data book will give you that. Or you can Google it. Oh, radius, right? Yeah. I'm good. Yeah, whatever the equation, you can find the right one. So what? Yeah. Anyhow, so radius of gyration also comes into it. Yeah. Okay, so that we know, and for this it was calculated at about 180 kilonewton meters for the experimental pile. Yeah, and then we obviously we had a aluminum pile, calculated the ZP for that, and the yield stress for and then converted that into prototype scale using the scaling laws we learned yesterday. So that is the limit. Now we are looking at slowly increasing my pile displacement here. So what is happening to MA and what is happening to MB? Because these are something we can measure in the experiment, right? So as the delta increases, it was going up, MA is going up there, MB initially goes up to there, and then MB reached its limit while this tries to increase. Obviously, it can't go past there, yeah, because that is you reach the moment capacity. Therefore, you would expect the failure to happen somewhere there, where at the top of the pile. Understood? And that will happen at a displacement of about 0.3 meters. So if my lateral spread is going to be 0.3 meters or more, my pile is dead. Agreed? So if I were to look at the width depth, the bending moment distribution, for different amounts of deflection, 0.1, 0.2, 0.3, you can plot this. Because the pile cap is so rigid, there's no change in, so that's pretty much zero bending moment there. But it will have, the pile will have some moment, which is my MA being applied. And that obviously is increasing with deflections. At the base, where we marked MB, you can also see these are increasing as we increase the deflection, right? So you can then mark where my MP value is and see who's coming closest. So that will tell you whether the pile will have a plastic hinge forming at the base or at the top. So accordingly, you can even adjust your pile reinforcement to make sure that doesn't happen. Okay? So, but that is structural detail. But this is the bit structural engineers don't understand. This is what we got to tell them. When they come and ask you for spring stiffness and stupid things like that, you got to show them this and say, no, it's not like that. It's like this. You go and design so that at the top of the pile, even with 0.3 meters, I get at least a moment capacity greater than 100. And at the bottom, it should be maybe close to 150. And then they can design. Because if you tell them sensible things, structural engineers can handle that. If you say, well, it's all complicated, then they'll run away and never come to see us. So that is for single pile. Yeah? For pile group, what's going to happen? Similar situation where we are now getting MA and MB all will line up because they're all like, you got the frame action. So MA and MB will be the same. Ultimate is drawn here, which means I can allow up to about let's say 0.35 meters of deflection. By that point, I will reach my full plastic moment capacity. Yeah? So we'll do the same thing, different levels of deflection of the pile cap, 0.1, 0.2, 0.3, and you can see it goes first for 0.1, it's okay, 0.2, maybe okay, 0.3, it died. Yeah? And it dies because MA and MB are both the same because of the frame action. Both will form hinges. So the pile will die by forming a hinge on the top and a hinge at the bottom, like what I've shown in the very first slide. Okay? Now we got the proof, and we can also tell how much deflection it can tolerate by the time it gets. This is all pure structural analysis. Yeah, we haven't done any magic with this. This is how much structurally I can deflect to get the failure or plastic moment hinge formation. Whether there's a bit of an esoteric question where you can say if the plastic hinge forms within the pile, would you call that failure or not? Now that is way beyond where we are now for piles. Normally, when you're doing pile design, if they formed plastic hinges, you'll say tata bye bye, the pile has had its day, right? However, more recent British standards and probably Eurocode as well, they are allowing plastic hinge formation in retaining walls, steel retaining walls, because even suppose you know what retaining wall is. I got soil this side, excavation this side. Even if I form plastic hinge at this level, it will deflect. But to deflect this, I need to spend energy in rotating the hinge, right? So I still have some more extra capacity. So what they want to say is that can you utilize that extra plastic capacity as well by allowing some more deflection? Okay, as long as the wall doesn't collapse, you're okay, right? If I got more tip deflection at the top of the retaining wall, maybe it's okay. So that's happening in retaining walls. It hasn't come as far as piles yet. The problem is retaining walls, if the top deflects, you probably don't care that much. Okay, yeah, instead of 0.05 meters, it deflected to 0.1 meters. Nobody is going to die, the wall is not going to collapse, it's all okay. Problem with piles is, once you reach the plastic hinge, that means I undergone already 0.3 meters for this particular case, right? Then the P delta effects start to dominate, because I still have to carry the axial load. So the worry is that although I have this plastic moment capacity, the more deflection I give, the worse it gets, the more the P delta moment will become. So therefore, that hasn't percolated to these, and nobody has done enough research to say after the plastic hinge is formed, how much load, how long before I will completely collapse the pile. So there are reasons for it. Sorry. Anything you're not sure about so far? This is a little bit heavy duty stuff. That's why I thought we'll have lunch and come back and go through it. And you've been asking for last 2 days, when are you going to teach pile groups? So there's a good reason why I had to cover everything else before I got here. Yeah? Okay. Now, as was the theme, it's one thing to do all that with no experimental evidence, but that's not my game. My game is to say, right, that is the theory or the framework we have. How much validity it has can only come from some experimental evidence. So this Jonathan Knappett, who is a professor now in Oxford, I must say, he's done very well. He done these experiments where we have piles, yeah, in going through liquefiable layer. We had some kaolin clay, which is pre-consolidated to have a given undrained shear strength. So the clay is homemade, or we make it ourselves. So we know exactly what strength it is. Then we had a liquefiable layer, relative density of about 35. Add some water here somewhere. So thank you. So we know when we shake, that will definitely liquefy, and below that we have dense sand at relative density of 85%. And to do this accurately, somebody was asking yesterday, how are you sure that you get this relative density? We built a machine which can pour the sand to the density you want. So you tell the program how much, the speed at which it pours, and you will get the right relative density. So to do one piece of research, you need lots of kit, and we also needed the laminar box. So a lot of things have to fall into place. Anyhow, here we are, geotechnical engineering. So feel free to have a look. And lots of instrumentation as well. So, one of the things, I can put acceleration, one was 0.2, the other one was 0.26, but as I said, these have very little influence on the liquefaction. Once it's above 0.1 g, it will liquefy the soil. So that's not a big deal. 2.25 meters and 3 meters. Okay? Not of the pile, sorry, the slope. But the loads are, one is 345 kilonewtons, the other one is almost, it was 1155 kilonewtons, which is a factor of 3 times more, roughly. So, we are deliberately going past what normally people would use as a factor of safety in pile design. Pile design, normally you apply a factor of safety between 2 and 2.5. We said no, we will apply a load which is way above that. And what we are interested in here is the lateral load and deflection response. So this is the lateral load that is being generated, okay, and that is the deflection. So all these squiggly lines are the actual, so we are monitoring how much the pile is horizontally deflecting and also what is the load on it. So you're plotting one against the other. So they, of course, because there are 4 piles. And delta is the how much the deflection is happening. So at the beginning, horizontal load is 0 and deflection is 0. Again, classical clay behavior. So initially, it thinks it is quite stiff, and if you apply enough cycles, it softens. Please tell John. Next time you come into contact, say, no, I have seen, so no strain rate effects and all that jazz. We are applying at like good 1 hertz frequency here. So peak and then it softens. Yeah. What Jonathan also did is to look at the residue going positive and also negative, right? Upslope, downslope. Downslope, upslope. But what is the net effect of all this is also marked here, what he calls residual or there's a trans. So this is when we increased that by a factor of 3 roughly. Yeah. Here the residual, these are both, oh no, it's the same, yeah, they're same axis. It's just that this one is very asymmetric, right? Because it's starting there, 0, it's going very much positive up to 1500 and little bit negative, but mostly on the positive side. This means that the clay is driving the pile quite strongly downslope and not allowing it to go upslope. Yeah. Here we have this residual value somewhat less compared to this, yeah. But what is very clear is when I have more axial load, I get this positive side even bigger than that, but also it's more symmetric both upslope and downslope. Because the effect of the clay layer, the amount of load that can apply or force that can apply is relatively small compared to the axial load the pile is carrying. So whether the slope wants to go down or not, it still has to cope with the axial load. So that will oscillate because it got the inertia both positive and negative side, that is driving the piles. Okay? Right. So this is experimental evidence. Now, how do we sum up all this? So we got horizontal load, yeah, and we got deflection here. And we are putting data from different tests together. So what you can do is look at where the pile will undergo ductile response, yielding and ductile response, and where will it undergo unstable collapse or buckling type failure. So what we are saying is these are obviously, the blue line and red line are idealized lines. The actual experimental ones are in the black. Okay, they're not perfectly like that, but they're not far off. In fact, I would say it's pretty good. So if I make my axial load smaller, then I'll follow more or less the blue line, reach some peak, and I will get slow yielding of the pile, and it will continue to deform as the plastic hinges form, because my axial load is relatively small. When you have 3 times more axial load on the pile, it goes up here. First of all, it can't take as much H, undergoes some more deflection as driven by P delta, and then it will fail. It will reach its MP. And once this type of thing happens, it will reach the unstable collapse state. This is what I was saying in, I've forgotten, is it yesterday's lecture, where we said we did some abacus things, where I drawn, I'm pretty sure I've shown you this. So if you, in abacus using Rick's algorithm, you can get that kind of behavior. If you want to capture that kind of post-buckling behavior, you will see that I need to draw a circle around here, draw tangents, and then work out my way down here, iteration by iteration, and then you can follow post-buckling deformation behavior of columns. So that's what he has done for the numerical bit, but effectively that is for ego satisfaction, all this. For a practical engineer, once you reach this, as he has drawn here, crash bang, pile dead is about right. Okay? So what we just shown is, if you have quite a lot of axial load on the pile, you will buckle, and that is understandable. That's what we are saying. But if the amount of applied axial load is small, you will get this kind of yielding but stable ductile response. So no sudden instabilities. Right. Then we want to see how we can use this in design. So let's consider a pile, 0.5 meter diameter, length maybe 14 meters. When I say length, length in the liquefiable layer, EI of say 50 meganewton meter squared, round number, MP of about 160 kilonewton meter. Okay, these are the values. So here we are doing the load per pile. So this depends on, you got 2 by 2 pile group, 2 by 3 pile group, whatever it is. You work out the load that pile is carrying per pile. The group is carrying, but then you work out the force per load per pile. And on the x-axis, we are looking at the force the crust can apply. 1 meter thick crust, 2 meter thick crust, you can work out how many kilonewtons that it will generate. So I can go along here, and let's say I got something like 6 kilonewtons of the crust force. Then I can go up and see I can almost apply 900 kilonewtons of axial force, still not buckle. So this line marks the buckling line. Okay? If my crust force is more, then this value will come down. So very quickly you can check that will this cause me buckling or not in one figure. Yeah? Because this is not buckling in what you have done, where everything was level ground and it's all liquefying. Now you are in a slope with a non-liquefiable crust on the top. Yeah? You can also check what the pile deflection is, delta, compared to the load you're applying per pile. So, for different crust forces, 6, 18 and 30, 6, 18 and 30, these are plotted. The instability is about there. So, clearly we don't want to go as far as that. So, you can see, say I'm applying 400 kilonewtons force. So I can come along here and see for a crust force of 6 kilonewtons, I'll get a deflection of maybe only 0.02, something like that. If I apply 400 kilonewtons but my crust force is 18, I'll get deflection of 0.1. For the same thing, if the crust force is higher, I'll come down to about 0.18 meter. So we can say how much, depending on the crust force, we are deflecting the pile. Yeah? And we can also plot, I think there should be one more. No. Okay. This is the crust force here, deflection here, but for different levels of axial load you're applying. I haven't done anything. अरे यार, ये तो बेकार है. Hello. ठीक है. I mean, we're almost done, but thanks for the trying anyhow. If not anything else, it's quite amusing. So here we can see how these crust force and deflection get influenced by axial load. This work, as I said, is nearly 10 years old. Neither the Japanese nor the Americans, I don't think, fully understand what this means, and therefore it hasn't made its way to courts of practice. But it's been published. People read it. Other academics in the US and in Japan talk to us, call us, email us, and oh, that was good. How do we do this extra thing or something else? But really, what frustrates me is that the same old things keep getting circulated. The Hamada equation of empirically calculating the movement, when we know Newmark method works better, or this is a complete process. We know the failure mechanisms, we know what are the important factors in this, and here is the data to support it. You can't ask for more than this. And hence, the reason for the Gyan course is that at least you guys know this all exists. You may not pick up all the nuances of what is being presented here, but at least you can go back and read the papers, right? You can read the book, read the papers, and so on. But be aware that it is all there, and it's can be used straight for design. It's not something we made up. Now you can say, how will all this change if you've done this for 0.6 meters or 0.8 meter or 1 meter diameter pipe? Okay, if what happens if L changes and so on? Yes, this gives you a starting point, right? So then you can say, well, I got longer pile, then obviously my P crate will become more critical. That's common sense, right? I got more stiffer clay crust. The force F crust will go up. So you can, at least as a first point of for design, do that. Okay? Very good. So I'd like to summarize with this slide, where basically piles in laterally spreading soils suffer quite a lot of damage because of this kinematic loading imposed by the flowing soils. This is very clear. You got inertial load, but you also got this kinematic load, which is where we started all a few days ago. Single piles were investigated. We shown the inadequacies of design methods like the JRA 1991. Recently, I've been in Japan. They said, oh, we got 2015 JRA code. So this is all old news. I went and somebody gave me a copy of the new code, and I looked at the new provisions in the new code. They're exactly same as that. They changed the date of public. The closer piles will act as one large pile and rotate. Piles that are widely spaced will attract the flow of the soil. They almost act like single piles. The main point that I wanted to convey, and this is really the crux of the matter, is you cannot take piles in liquefiable soils and demarcate them as ones which carry axial load and ones which are subjected to lateral spreading. It's the same pile carrying the same load. So you need to consider the combination of axial and lateral load, and that obviously can push the piles either towards instability in one case, or if you design them more carefully, that should give you push the pile more towards stable yielding. And obviously my design recommendation will be, try and design your piles to suffer more stable yielding is always a safe design. In unstable, collapse is never is. Okay? Right. I think I entertained you suitably for today. It will be almost a crime not to ask you to do anything. So what I like you to do is to do this calculation, where use the same, you have access to these charts, right? So use exactly these, yeah, but so EI MP values are given there, and apply an axial load of half a meter, right? So 40 times 4, 160, 1600. So that's fairly lightly loaded pile for that diameter. Okay, and the slope, let's keep it the same, 6 degrees. And so work out, so bending moments. So I'm going to say, do you use CU or SU for underhand strength? CU is okay? Okay. CU of 50 kPa, and that thickness is 2 meters. Okay? And this is all going, I'm going to call that also 14 meters to match that. 14 meters of liquefiable soil, 2 meters of crust on the top. So work out the bending moments and tell us what the factor of safety against failure is. So bending moments, factor of safety against plastic collapse. Okay? Do you think you need any other information other than that? All good. If you feel you're missing some information, make assumptions and just write what the assumptions are. Okay? And I think Professor Agnihotri already said, tomorrow you need to submit all the bits I asked over the last 3-4 days. Very good. We finished ahead of time today. But there should be enough work for you to do. Yeah.
What was the residual force? There was a residual force plus transient force. What exactly is that residual force?
Residual force is like once the clay has failed, you got to the peak, yeah, or even for liquefied soil, you got to peak, and once the displacements are quite large, right, it can't. Initially, when it starts to move, it applies big pressure, and as there is more and more displacement, the force it can apply comes down, and that's what that down thing is. The Go and Rourke have that. What is the peak value? I think about 15% of mean confining stress, dropping to about 3% of the mean confining stress over a very small range. The thing is, it drops from that peak to residual in very small displacement. So the strains are very small.
Cyclic forces on the planet, which is corresponding to the gravity.
Yes.
Then there is a residual force one.
Oh, you mean in these ones? Yeah, yeah. No, this is just removing the cyclic component. Yeah, maybe I didn't explain that properly. So he marked it as residual, but basically what this is you form the cycles about a mean value, right? So this is what that mean is for that cycle. So say you got 1 point here. You look at where did that cycle go, there and take the average.
How the mean is what it was?
You take the max and min and take the average. It's just you are removing the cyclic component of it.
So the displacement will be proportionate to the mean?
Yeah. Because otherwise the cycles are going back and forth. You need somewhere you need to anchor your point. Yeah.
So in this, if we are having more extra load, it is not getting soft.
More extra load is showing it is not softening. Basically, what it's showing is if you put so much axial load on the pore pile, no matter what the clay does, everything is dominated by the load on the top. And that's why it oscillates like mad. It probably fails the clay both on the downslope and upslope side because it wants to oscillate both sides, but it got all that GPA, gravitational potential energy, the mass on the top. So that will push anything in its way, and poor little clay ain't going to do anything. Okay, that's what's going on there. Okay, anything else?
There was some PL, your derivation of limited equilibrium.
Yep.
There was a question PL.
Yeah.
So how to experience this PL? Like,
Well, I thought that's what you're going to do. You're asking me to solve my problem. You have various ways, right? One way is go back to the Go and Rourke. Yeah? Because that is the curve they have shown. You can pick from there. Yeah? One option. Other option is this one. Look, I'm not going to tell you how to solve the problem. You have a go. If you can't do it, we will have a go tomorrow. Otherwise, what's the point?
sir, there is one general question.
Yeah.
Like before liquefaction, suppose we have some properties of soil. We have particular pH curve, we have an angle of internal friction. Now, during liquefaction, these properties will change. The pH curve will be something else.
Yeah.
Then psi will almost be negligible. And then after liquefaction, will you get back to original properties?
I mean, post, long time after liquefaction. Are you talking about post consolidation?
Like after a week maybe.
Yeah, okay. Yeah, you're talking about post reconsolidation after the liquefaction. The belief is yes. In fact, if anything, you'll get better because if it is sand, it would have densified, right? So you'll get better resistance than before. During liquefaction, one of a current project we are doing is we got a monopile, we liquefy the soil and pull the monopile through the liquefied soil before the pore pressures are dissipated. The results are yet to come, but that's something we are trying. But I think I showed you the data for before and after liquefaction in one of the centrifuge tests. That's the paper we published in Bulletin of Earthquake Engineering. The chap is called Seong, Abadi, myself, and Haig. You can look at that paper. So we clearly post liquefaction reconsolidation, the lateral capacity of the monopile increases because the soil has densified. All right? Anything else? Very good.